As an example of the kinds of things you can do with just taking partial derivatives and playing with the math, let's look at this. This is equation 426 of Ball. Where did that come from? Well, just let's see. Follow along in Ball, but those of you who don't have the Ball textbook, I'll just start here. You start with the definition of G. G is defined as H minus TS, and H is defined as U plus PV minus TS. Let's look at this. Volume and entropy. Volume and entropy. Look at this down here. Volume and entropy. You can associate volume and entropy as derivatives of, so let's just go ahead and do that. So this is equal to U plus P, how G changes with how G changes with P at constant volume. Did I get that right? Let's go back here. Yeah, how G changes with P at constant temperature. G changes with P at constant temperature. And minus sign in there. Minus T, and now we can substitute in for entropy. The entropy is how G changes with T at constant P with a minus sign in there. How G changes with T at constant pressure times a minus 1. So all we did was substitute in. Let's see, we have G over here, and substitute in there. So where are we going here? Well, we want to have du on the left and dg on the right plus derivatives of dg on the right. So let's put u is equal to g minus p, how G changes with pressure at constant temperature, minus, and anticipation of things here. Let's put the P on the other side here. Put that over there. That comes to be a plus how G changes with temperature at constant pressure times temperature. But that was a plus, and that was a plus. So this must be a minus. Minus, but then you're putting it over on the other side of the equation to isolate u. All right, now let's take the differential u, that'll be just dg, minus how G changes with pressure at constant temperature. This is just some number, so you don't have to take the differential. That comes out of the differential times dp. How G changes with temperature at constant pressure times dt. So that's how one starts with the definition, how one gets this equation 426 of Ball. Now let's derive an analogous expression for u, assuming you know the behavior of A, how A varies with temperature and volume. So instead of u, we're going to do A. Here we did G. Let's now do A. Start with the definition. A is defined as U minus TS. And let's see, we have A. Well, let's go ahead and isolate U. We want an analogous expression. That's equal to A plus TS. All right, let's go back to our handy-dandy table. Here is A. And what do we have there? We have a T and an S. A looks like we're going to take a derivative with respect to temperature. Minus S is how A changes with temperature at constant volume. So we're going to isolate that. That's equal to A plus T. And don't forget there was a minus sign there. How A changes with temperature at constant volume. Take the differential. du is dA plus, and we'll put the t over there. This is a constant, so, and that's a minus sign there. So I have to put the minus sign there. Minus how A changes with temperature at constant volume times dt. So there's the analogous expression, how A changes with temperature at constant volume. Now if we look at the problem, it said, assuming one knows behavior of A is it varies with T and V. Well, we really don't know. We don't have to know how it varies with V. In fact, you just have to know how it varies with T, temperature. So those are the kinds of things that you can do using natural variables and partial derivatives. So we'll continue along this line in the next part of Lecture 8.